Hi everyone, my name is Yifei from UPenn Grasp Lab. Our SymSkill co-invents symbols and skills to solve long horizon manipulation with minutes of data. Long horizon manipulation is difficult. When a robot is given a goal, it must figure out the correct sequence of actions to achieve it and how to control the motors in each action. There are basically two philosophies in solving this. Generalist policies, such as pi series, trained on millions of demonstrations, perform well for the goals they saw during training. But genuine compositional generalization, reusing known skills to solve a task you've never seen end-to-end, has not been shown. For now, they rely on VLM to do planning, and the data cost is enormous. Task and motion planning, such as Piddle Stream, takes the other route. It splits the problem into high-level task planning and low-level motion planning. It gets compositional generalization cleanly, but it scales poorly. Every new action needs handcrafted precondition, effect, and skill. And online, it cannot replan fast enough to recover in real time. Our approach inherits the strengths of both philosophies, achieving long horizon manipulation from only minutes of play data by discovering symbols and reactive skills directly from the data. Our method works in 3 steps. In data collection, as shown in the video, the human interacts with the object in the scene, doing any valid actions without a particular order or goal. Meanwhile, we track the type and pose trajectory of every object. We then segment demonstrations based on when objects start and stop moving, represented by the color segments on the timeline. At the end of each segment, we find relative pose between the grasped object and the reference object. For example, for the blue segments, when closing the lid, the pen is the reference object for the lid. Sometimes, which object is the reference object isn't obvious and requires semantic judgment. So we feed the images during the segments to a VLM and it identifies the reference object for us. All orange segments here are grasping food and have a pen as the reference object. So those segments gets learned as one high-level action called add food to the pen. Then we look at the beginning of those segments to find what is in common as the action's precondition. Here, the lid being open naturally is discovered to be the precondition of adding food to the pen. End effector trajectory during the segments are used to learn the skill to control the end effector. We visualize all 13 demonstration segments of putting food to the pen. We use a policy class called SE3LPVDS, which use GMM to learn mixing functions, linear parameters, and a tractor to achieve complex motion in reference object's frame in both Cartesian and rotation space. The different colors are the Gaussians discovered. On the right are the rollout of the policies. The axis is the stable attractor of this skill. This class of policy comes with guarantee that even when starting outside of the training distribution, the end effector will converge to the goal. The data efficiency of this method is the key to allow us to learn all skills with just 5 minutes of data. For this scene, we learn 11 actions, each paired with a skill. Online, with one or more goal specification, we can plan with the learn action using a search algorithm. Here, with the goal of moving the banana to plate, the 4-step solution is grasp lid, place lid on rack, grasp banana, place banana. During execution, we use the object's relative pose to track if preconditions for the current action are still satisfied. In the animation, you will see that after the first planning, the robot starts executing, and when the human disturbs, the robot replans and continues to finish the task despite disturbance. SymSkill in general is robust to disturbance in 3 ways. A small disturbance, the robot just keeps executing its stable policy. When an obstacle appears, we use a technique called modulation to morph the velocity field around the obstacles, so no replanning is necessary. Only one symbolic precondition break, we replan. Now all we change here is the goal, and also the scene has an additional food object. In this difficult situation, the planner can still plan in real time and figure out the 10-step plan to achieve the goal of moving everything in and close the lid. We benchmark SymSkill on RoboGasa 1 with its original demonstrations. Across 12 single-stage tasks, we achieve 85% success from just 5 to 15 demos per task. We ran 2 ablations. One is to remove online planning, and that performs not as well since many grasps can slip and need regrasping. The other ablation is to swap our stable skill for a state-based diffusion policy, and it starts on little data and fails most tasks. The other use case of our method is to learn from single-stage task, here open cabinet, pick and place, and close cabinet, and apply the learned skill and symbols on a new task of put the cheese in the cabinet and close the door. The algorithm correctly sequences these steps and first open the cabinet door, place the lid, and then eventually close the cabinet door. That is SymSkill, the compositional reactive learning method that is certifiable and data efficient. Our code is open sourced. Thank you so much.